And we're back. How are you doing? Well, I just got off the phone with you, so let me position the phone in a way where it won't be interrupted. So today we are going to be talking about some equilibrium stuff related to your problem set. The way I'm going to break this down is I'm going to go through this step by step, question by question. I'm going to touch upon the main topic in each question, and then I'm going to kind of give you a detailed explanation on how to approach the question, how to answer it for future reference. So let's dive right into it, right? Let's start with number one. So number one is asking us, sorry, I'm going right here. So it's asking us the equilibrium between carbon dioxide gas and carbonic acid is very important in biology and environmental science. It gives us the expression, and it asks us which of the following is the correct equilibrium constant expression, Kc, for this reaction. So in order to do this, the major topic for this, right, is just equilibrium expressions, right? We're gonna say EQ expressions. And then there's a couple important things I want you to note whenever we're doing these types of expressions. And one, you're always gonna write products over reactants. That's generally always how it's going to go. Products over reactants. And then you always want to make sure you put them in brackets. So whenever you put them in brackets, it's so you're going to put products over reactants and you're going to put them in brackets. That's generally how it is. If you have, let's say, for instance, like this isn't going to be a balanced expression, but I just want to do this for the sake of doing it. Say like this goes to 2OH plus H2 or something like that. Actually, I think it might be balanced. H2, right? If there is a coefficient, you're always going to put coefficient is always going to be the exponent. Right? And then so for this case, it'd be like H2. You don't put subscripts in on the coefficient. You don't put subscripts in the exponent, and it'd be like OH squared over H2O squared. And then the last important thing I want you to know is that you're always going to exclude liquids and solids from equilibrium expressions. And the reason for this, just a brief kind of overview on why we do that. Solids don't really affect the equilibrium, right? If I were to put, let's say we have this reaction taking place, and I'll just put a block of metal in there, and it's solid state. It wouldn't do anything to the actual reaction. Same with liquids. Like if you look at the expression, it gives a CO2 an aqueous solution, H2O as a liquid, and then the carbonic acid as an aqueous solution. So generally, liquids are always going to be the solvent. And as you'll probably, if you take organic chemistry in the future, you'll see that the solvent doesn't really. It's just there because it's a good solvent, and it doesn't actually do anything to the reaction. So with that in mind, looking at our expression, we see that there's no coefficient, so we don't have to worry about any of the exponents, right? And we know that we have to put products over reactants. So what we're going to do is we're going to say Kc is going to be equal to bracket carbonic acid, since that's an aqueous solution, and then since H2O is liquid, we can exclude that, and then we can just write CO2 on the bottom. And then that correlates with answer B, I believe, or C. Sorry, the lettering's a little weird. Yeah, so answer C, that'll be our our final expression. So 2. Let's go on to number 2. So number 2 is asking us a reaction with an equilibrium constant of Kc equals 1.5 times 10 to the negative 25th would it consist of which of the following at equilibrium? So major topic here is we're interpreting the magnitude of the equilibrium constant. So a very small Kc. So so basically less than 1. Or did the other way around. Less than 1 means it, not if, sorry, Vinci way, means it favors the reactants. And then a very large Kc is basically greater than 1, favors products. There's a lot more nuance to this, but I think this is just kind of a good way to remember it since your exam is on Friday. And then kind of just going into the answer. And then you can imagine if the equilibrium is 1, it's not going to favor either or. So the answer, right, since we see that the equilibrium here is listed as 1.5 times 10 to the negative 25th, that's basically 0.0 and then like 24 zeros, 23 zeros, and then 1 5. So it's going to be a lot less than 1. So we're going to say it's going to favor essentially all the reactants. Now, there's a note that I want to add to this, right? Because it does say, like, oh, well, some reactants and products with reactants slightly favored, some reactants and products with products slightly favored. They will give you clear explanations on that. Like, if you see it, like, say, 1.5 times 10 to the negative third, that's just, like, 0.15? One, two, three. I still have to do that, right? And that's significantly less. So you'll always see that disparity. There is a cutoff. I would say it's around probably like 10 to the negative eighth in my experience. I know there's actually like a concrete cutoff, but I don't know it off the top of my head. But you will be able to definitely see the difference between 10 to the negative third and 10 to the negative 25th. Very big difference. So in this case, it's going to be essentially all the reactants are favored. And this reaction is actually most likely not going to happen. So let's go on to number 3. So number 3, is the major topic here is going to be, we're just going to say the conversion of the equilibrium constant to equilibrium of gases, right? So there's actually an equation that we can use for this, right? And pretty handy. So the equation is Kp. It's going to be equal to Kc. So that's just our equilibrium constant. RT, which is rate constant temperature in Kelvin. And then the change is delta in moles. Moles we abbreviate with N. So just to kind of give you the components here. So N is going to be equal to the number of moles of the gaseous products minus the number of moles of gaseous reactants. Right? And for this rate constant, we are going to use this R. Generally, it's going to be this R. It's going to be the 0.08 0.206 liter atmosphere per mole Kelvin. Sorry, I'm just looking at the equation right now. Mole times Kelvin. And then make sure you convert to Kelvin for your temperature, which is 273 plus however many Celsius you have. So I'm not going to run through, just for the sake of time, I'm not going to run through the calculation, but you have everything you need. You have, it would to set up the equation, it would look like this. Be 1.5 times 10 to the negative third. Oh, sorry, I'm looking at the last one. Oops. So it's 2.1 times 10 to the negative second. And then that's the rate constant. I'm not going to rewrite that. Temperature is just the Celsius plus 273.15 if you want to be more exact, but most people just say 273. And then based on this, we know that there's 3 moles of gaseous products and 2 moles of gaseous reactants. So we're just going to say 1, right? So we can even exclude that. And then from there, we can figure it out. You can run this through a calculator and get the final answer. So moving on to number 4. So number 4. So the major topic here is going to be reversing reaction equilibrium concepts. Constants. Almost forgot to spell that. So, right. So when we have this equation, right, like x plus y, and we can kind of denote it like that, equals some product, right, like b. We can always say that we know the Kc, right? And that's going to be some number. Let's say that's A. However, since it's a reversible reaction, there's actually a mathematical relationship between the two. And we can generalize this by saying the K of the reverse of the reaction is going to be equal to 1 over the forward. Right? So if we know already what the forward is, it makes this pretty easy. So it says in your problem set that the forward is 5.0 times 10 to the fourth, right? And then it's just asking us to reverse it. So we can just say that's going to be equal to 1 over 5.0 times 10 to the fourth, and then you can just do the math from there. So when they say, also another note, don't get tripped up dude, go check your fucking pen. That was Vai com this.
Are these my spot?
I'll be using them for the time being. I know you will. Sorry, I hope I caught that on the voice, the voice recording.
I'm curious if you did.
Yeah, I mean, I'm sure I did. I'm sure the neighbors heard it. All right, sorry, that was insane. So don't get tripped up by the temperature in these types of questions, right? 25 Celsius, generally just room temperature. And the temperature has no bearing on asking us what the reverse of the reaction is. So, go on to number 5. So, now we're kind of introducing this this concept called Le Chatelier's. Le Chatelier was another one of the virgins of chemistry who fucking had way too much time on his hands. And his principle, to kind of sum it up, he basically says whenever there's a change in pressure, temperature, concentration, or even I think also catalysts fit into this too. But the big ones are temperature, pressure, concentration. That's going to shift the equilibrium by some by some degree, right? And that's why we have ice tables, and ice tables kind of help us see how that is going to shift whenever there's a change in concentration. But this isn't asking about it, so let's not hit on that right now. So the major topic is also going to be Le Chatelier's principle. So I'm just going to arrow up to that. Okay, so let's break down how to solve. So the reaction that's given to us is this 2NO bromide. Sorry. And then that reacts to form, I just write this double-sided arrow. Don't tell any chemists, they'll get mad at me. 2NO gas plus this bromic gas. And then it gives us the delta H of the reaction. So the enthalpy of the reaction is positive 30 kilojoules per mole. Right. And it also gives us okay. So a couple of things just we can get from this. And this just whenever they present something like this, especially if it has a delta H, what can we notice from here? Right? So if we recall, the enthalpy is a change of heat in the system, right? So if we're seeing a positive change of heat in the system, that means heat entered the system. So that means this reaction is going to be endothermic, right? So think when you see a negative delta H, that means heat left the system, so that's always going to be exothermic. Positive means that heat entered the system, that's going to be endothermic. Okay, so if we were going to shift, right, so this question is basically asking us, what will cause this reaction, this will cause the equilibrium of this equation to shift to the left, right? So in essence, it's asking us, how do we shift this to the reactants, right? Well, there's a couple of things that we can do, right? So if we decrease, I'm just going to write these down, kind of explain them after I'm done writing these down. If you decrease the container volume, ooh, spelled volume wrong. There goes my college education. If we decrease the container volume, that means that shifts equilibrium toward fewer moles of gas. So that's going to mean we're going to shift it left. If we remove products, that's going to shift equilibrium to the right, which is no bueno. Now, if we add more reactants, that's going to also shift to the right. So that's also no bueno. Now, if we lower the temperature, that's going to favor the exothermic direction. So that's going to shift it left. All right, let me just pull this up. Just checking something. 1 second. You can skip through this part of the video. Okay. I misspoke on this one. This actually shifts to the right. Oopsies. All right, so let's go through. Oh, sorry, I was just looking up, just kind of making sure on Le Chatelier's. It's been a while since I've seen it, so okay. So if we increase the container volume, there's a couple things that's going to happen. Number one is that's increasing volume, right? Increasing volume is going to decrease pressure. Right, so like if we visualize this, let's say we have two containers, and then say we have some liquid here, and we have some liquid here. Now, in red, we have kind of this gas, it's kind of like floating around everywhere, and that's going to create our pressure. The more liquid we have, the less gas there is, which means there's going to be less pressure in that system. So increasing the volume is going to decrease the pressure. And reactions, they don't like that, right? They're going to try to counteract that. By shifting towards the side with the most gas moles to increase the pressure. And we see from up here our equation, we know that there's 3 moles of gas, 2 moles on the left. So we know it's going to shift to the right. So we're not going to like that. And that's not going to be a correct answer for this. Now, if we remove some of the product, right? And let me draw an arrow down here. So if we remove product, the system's going to be like, wait, where'd you guys go? I'm actually not going to write it down. Right, so if we remove the product from a system, what's going to happen is, you know, this equilibrium constant And this equilibrium of this reaction is going to be like, wait, where'd you guys go? I miss you guys. Let me make some more of you guys. So that means it's going to increase the production of the product. And since we know that we want to shift to the left, to the reactant side, we don't want to be making more product. We don't want to put that stress on the system where it's going to just start, kind of spamming out this product. So if we remove the product, right, then the system will try to make more of it. So we know that by this, we cannot, that's not something that we want to do. So same goes for C, right? So C is asking if we remove some Br2. Right, they're both reactants. They're both products. I misspoke there. Right, so we remove NO or Br2, right, then the system is going to have this absence of product, and it's going to try to make more, and it's going to shift it to the right. So the last thing we can do is decrease the temperature, which, forgot this one, D. Adding more reactants. So if we add more reactants, that's just going to mean the system will try to make more products, right? So, it's kind of a little counterintuitive, right? Because we say, well, if we take away these products, then the system's going to try to make more. What if we just add more reactants? Well, if you're adding more reactants, all you're really going to do is you're going to add more stuff that's going to react with each other. And if you have more stuff in the system that's going to react with each other, that just means that there's a higher probability that you're going to get a lot more products. So that goes to show, if you add more reactants, that's just going to make more stuff to react, and that's going to shift to the right, just because you're going to have this increase in the amount of products that you get in, the amount of products that you're going to be making. So this is also going to shift to the right, so this isn't good. And then, so the last one we have, right, is decrease the temperature. Right, so if we decrease the temperature, remember what we said at the beginning, it is an endothermic reaction, right? So that means that the reaction needs heat to happen, right? Because when this reaction happens, it takes in this heat, and if we go back to kind of our Hill diagram, right? So if I draw this out real quick, where you have, this is your reactants, and then there's this hill, and then you have your products, right? It needs to get over this hill, and it needs some energy, right, in order to get over that hill. Now, if you decrease the energy, what's going to happen, it's going to try to go up, and it's not going to make it because it needs that heat in order to get over it. So because of that, we need heat. Therefore, if we have an absence of heat, then we're not going to get as much product as we had before. So that's going to shift it to the left, right? Because if we can't make the product, then that means we're just going to have more reactant, and the equilibrium is going to lie to the left. So E is going to be our correct answer. And another way you can think about this is, in an endothermic reaction, heat acts like a reactant, right? And in an exothermic reaction, heat acts as a product. So if the temperature decreases, equilibrium shifts to the side that produces heat, and the exothermic direction, opposite of the reaction direction, and thus the reaction shifts towards reactants, which is the left, which produces heat to counteract the loss of heat. That explanation might be a little convoluted. Just listen to what I said earlier. I think I might have explained it a little bit better. All right, so let's go. That was number 6.
Never mind.
Yeah?
My parents just landed.
Your parents just landed?
Yeah.
So what, it'd be like an hour? Are they coming straight here?
They want us to meet them at the Embassy Suites.
Where's the Embassy Suites at?
Get my phone.
Okay, I'm gonna speed run through these next ones because these ones are. Okay, these next two ones are going to be involving ice tables.
It's 30 minutes by train.
Okay, do you want to leave here in like 20 minutes? So we're gonna label this one calculation 1. So this is gonna be your next, and the major I would say the major topic here are just calculating equilibrium concentration. So it's just ice tables. So I'm not gonna write that down. But let's start off with writing the reaction. So our given reaction is H2 gas plus CO2 gas reacts to form this water and gas, and then plus carbon monoxide and gas. And then it's given us that the Kc equals 4.2 at 1650 degrees Celsius. So my approach to this is kind of write down the information it has, right? So it gives us that we have 0.8 moles of H2. And then it gives us, we have 0.8 moles of carbon dioxide. And then we know that the volume is going to be 5 liters. And then if we do our molarity concentrations, right, our little, if we remember, all this is going to be done in molarity, right? So that's just moles over liters, so 0.8 over 5, and then that's going to be equal to 0.8 over 5 liters, moles, liters, and that's just both going to be equal to 0.16 molar. So first thing you're going to do is calculate molarity. That's going to be the first and most important thing that you want to do. Now the next thing that you want to do is you are going to start setting up your ice tables. So another thing important to note is that we don't have any initial H2O or carbon monoxide, right? So we can say that both of those are going to be at 0. So
They got delayed and they just landed.
Initial concentration,
So Ramon and I, they have like they're staying at the Embassy Suites.
and then
Go with Ramon and I.
equal,
Probably like 20 minutes to get over there.
and then H2, we're going to write this on the side, H2
Not long at all.
CO2, and then we're going to write H2O. So you're always going to write your reactants first, products under it. That just makes it a little bit easier. All right, so what's our initial in molarity? All this is molarity. So we know we have initially 0.16 of both of these, and then we don't have any products, right? Because this is at the beginning of the reaction, so we're not going to have any products yet. Concentration, right? Once we let the reaction run, this is going to go down by X. We don't know what X is yet. We're going to solve for that. This is going to go down by X. This is going to go up by X. And then this is also going to go up by X. So our equilibrium expression is going to be 0.16 minus X, 0.16 minus X, and then 0 plus X is just X, 0 plus X is just X. So now you're probably thinking, what the heck, how do I set this up? Well, we're going to set up the expression, right? So Kc equals products over reactants. And I'm going to save you the time. None of it's going to be liquid or solid. So we can say Kc is going to be equal to H2O times CO over H2 times C2, right? Because those are our products over our reactants. And that's all going to equal 4.2. Remember, that's what they gave us at the beginning. So then we're going to simplify this. We're going to say Kc, and we're going to sub in what we have in the ice table. And we're going to say Kc is going to be equal to X times X all over 0.16, minus X squared. And this is where your algebra is going to come in handy. I hate to tell you. So that's going to be equal to X squared over Since there's two of these, I kind of jumped the gun here. It'd be 0.16 minus X times 0.16 minus X, right? So those are our two products, right? Remember up here, we have that these are X, and then our two reactants up here, we have that it's 0.16 minus X. So that's gonna be equal to 0.16 minus X squared, and that's gonna be equal to 4.2. And what we're trying to do here is solve for X. So, and I'm just going to put this into my calculator, my little ChatGPT calculator, and just so I can kind of see a detailed breakdown. All right. So this is the hardest part with this is not setting it up, but it's the algebra. Because the algebra can be a pain in the ass, and I'm sorry to say that, but it is. So what you're going to do here is first you're going to FOIL this out. So you're going to say, okay, 0.16 minus X times 0.16 minus X. And then hopefully it catches up with me. And that's going to be equal to 0.0256 minus 0.32x. So you're just going to FOIL here, times x squared. So you're just basically undoing this, right? You're multiplying these two together. So now we have this expression. We have x squared over, I'm just going to call this y. So x squared over y equals 4.2. To simplify this, we can just go here and we can say x squared equals 4.2 times y. And now what we're going to do is we're going to just distribute that 4.2, and I'm just going to write it down again. So 4.2 times 0.0256 minus 0.32x plus x squared. So stay with me. So now we're going to distribute this 4.2 to all of these terms, and that's going to leave us with x squared is equal to 0. And you can see all of this in your calculator. This is why it takes a little bit of time. 0.10752 minus 1.344x plus 4.2x squared. And then what we're gonna do now, sorry, this is a lot of shit. I really apologize for this because this can be a pain in the ass. But now what we're gonna do is we're gonna move this x to this side, and since it's positive over here, we're just gonna subtract it. So it's just a lot of algebra. I apologize. So 0.10752 minus 1.344x, and then plus 4.2x squared. And since it's the same variable, and we know that the coefficient has 1, it's going to be minus 1x squared. So that's going to leave us with 0 equals 0.10752 minus 1.344x, and that's going to be plus 3.2, right? Since we just subtracted it by 1. And we can just arrange this into the quadratic form. And I'm going to bring a term that you probably haven't heard in a while, and that's a quadratic formula. Some calculators have this kind of formula already embedded in it. I would check to see if yours does, because it could save you a lot of time. I don't even really remember the quadratic formula. I think it's like negative b. It's like, what is it, like plus or minus b something shit. Fuck, I don't know. But the quadratic formula, oh, okay, sorry. This calculator caught up to me. So it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, right? And then we know a is going to be equal to 3.2, b is going to be equal to 1.344, and then c is going to be equal to this last number, 1.10752. So okay, so now we're gonna solve, and you can plug these into a calculator. These are my two x's, right? Remember, plus and minus means we're gonna get two answers. So x equals 0.075 molar, and then x equals 0.3125 molar. And then with this, the final step is we have to check the viability. We got to see only one of these is going to be right, so we got to see which one it's going to be. So final step is going to be check viability. So what we're going to do, right, so we know our original expression was 0.16 minus x for the reactants. And for the products, it was just going to be x, right? So since we know it's just going to be x, we can kind of exclude the products from this, and we can just focus on the reactants. So now let's start subtracting them. All right, so 0.16 minus 0.1075 is going to be equal to 0.0525 molar, right? And what does that mean? It means it's positive. And I'll show you why this is important here in the next step. If we try the other number, 0.126 minus 0.3125, I don't even have to do that out, right? Because we know that's going to give us a negative number. And you can't have negative reactants. That doesn't make sense, like physical sense. So we know that this is going to be our correct answer. So to sum it all up, it's asking us what the change in the concentration of each species at equilibrium are going to be. So we know that for our reactants, that's going to equal 0.0525 molar. That's going to be the concentration for the reactants for the products. It's just going to be equal to x, which we know x is 0.1075 molar. And that's going to be our final answer. It's actually funny, this little smiley face, my calculus professor told us in class that a smiley face is what he uses at the end of his like proofs that he publishes in papers, because it's an accepted ending to a proof. like sometimes they put like two swords together, but he has published like 40-page long like mathematical theory proofs, and he puts a smiley face at the end of it. So it's kind of cool. But those are going to be our two answers right there. So the last question is going to just be asking about Le Chateliers, and we kind of talked about that before. So I kind of want you to see if you can get that last one by yourself. If you have any questions about that, please feel free to reach out. I'm just going to give you a hint. It's going to be an endothermic reaction. It's going to be very similar to the last one. So, yeah. But the ice table, I would recommend going back through my explanation and my proof on that. The hardest part is going to be not necessarily setting up the ice table. I feel like for me at first that was like pretty intuitive. The hardest part is always going to be the algebra. Once you got the algebra down, these become really easy because you're going to do them a lot. So if you have any questions, please let me know. I'm going to post this to YouTube, and I'll talk to you later. I love you a lot.